with homework questions. What do you guys got? Questions from homework. I am open for business. Giselle, 49. You guys love these crate problems. All right. Here it says a crate weighing 50 pounds is being pulled up a ramp at an angle of elevation of 48 degrees with a force of 150 pounds. The ramp has an angle of elevation of 35 degrees. What is the amount of force being directed up the ramp? So, important question to lead off when you read this problem. How many vectors do you hear? Hi. Elena, it's for you. It's a good one. It's a get out of jail free card.
Oh, really?
Or early card anyways.
Yes. Thank you.
You're welcome. So when we read this problem, how many vectors do you hear? I hear 3. 3. So I have one vector for gravity because the crate has some mass to it. I have one vector for the pull being exerted. And then I have one vector for the ramp that we're going to be projecting onto. Everybody okay with that notion? So let's resolve these vectors into component forms. So gravity is just going to be the vector 0, negative 50. Since we're told the magnitude of the gravity is 50 pounds, and gravity points straight down, that's the vector 0, negative 50. Everybody's cool with that? Just from a common sense standpoint, we can probably say that. The next up is the pull vector. We're told that has magnitude of 150 pounds and a angle of, or direction of 48 degrees. So we'll just resolve that into component form by doing cosine, or magnitude times cosine theta, and then magnitude times sine theta. And then our ramp, the only thing we're told about the ramp is the direction of the ramp. So we're going to assume the ramp is a unit vector, which is nice because that opens up our shortcut to us. So resolving that unit vector into component form, we just do 1 times cosine of the angle, comma 1 times sine of the angle. So those are my 3 vectors that I read when I hear the problem. What are we being asked for? We want the amount of force directed up the ramp. So we're going to be projecting onto the ramp. What vector are we going to be projecting onto the ramp? P plus G, because both those both those vectors are forces. They're both interacting with the ramp. They're going to interact in a summative fashion because that's what forces kind of do. The nice part about this is, though, since R is a unit vector, I can just turn this into the dot product of R with the vector P plus G. And just take the absolute value of that. Everybody's okay with that? So what am I going to do here? I'm going to do Rx times Px plus Gx plus Ry times Py plus Gy, where the x subscript is just indicating that it's the x component of that vector, and the y subscript is just indicating it's the y component of the vector. And I'm just going to type that into my calculator now. I'm not going to bother writing the numbers there. Although if you wanted to, you're welcome to do that. It's not wrong to do that. Make sure that I'm in degree mode still. Good. So cosine 35 times, and then I have 150 cosine 48 plus 0, and then plus ry, which is sine 35, times, and then we have py, which is 150 sine 48, plus, and then gy, which is negative 50. And so I get 117.48. And that's my answer. And again, like as you're doing a problem like this, if you wanted to add P and G together and just get that vector in component form first before going through this rigmarole, that's fine. Not wrong to do that. Just feels like it's all going in my calculator anyways. I'm just going to do it in a way where I can just type it all into my calculator in one shot. Giselle, does that feel better? Yeah. So the key here is that the crate has a weight also. That's your cue that there's going to be 3 vectors going on in the problem. In all the previous problems, it was like a crate of negligible weight, meaning that there is no force due to gravity. Here, because the crate has mass, there's a third force or third vector going on, the gravity vector, or vector due to gravity anyways. Is that okay, Elena? Sure. Okay. So here it says, find the intersection of the 2 lines if it exists. So the if it exists part tells me that it's possible that these 2 lines could be parallel or coinciding. So I'm going to do like the full check before I just dive into just finding their intersection, because I don't know if they're intersecting once, infinitely many, or not at all. So the first thing I'm going to check to see if if we're parallel or coinciding. To do that, what I'm going to do is I'm going to take the slope vectors and see if one slope vector, is like a scalar multiple of the other slope vector. So when I do that scalar multiplication, I just get 2k, 4k. And this is equivalent to the system. 2k is equal to 3, and 4k is equal to negative 5. If I solve for k now, these k's are different. That tells me the answer to this is no. The slope vector is not the same, meaning the lines have to intersect. They're not coinciding. They're not parallel. I'm safe to now proceed to find the intersection. Is that good so far, Elena? Okay. Well, if you don't know that they intersect, which we don't know that square away, otherwise kind of weird things can happen when you try to solve the system we're about to set up. And I want to just, it's easier if you know from jump, oh, something weird is happening here, because it saves you from having to solve a system. It's an easier process than finding the intersection. So it's a time saver. And in all reality, Giselle, like looking at this, you can tell just by looking at the two vectors, right? That obviously one is negative, and the other is not. There's no way I can multiply by the same k to two positive numbers and get one negative and one not negative, right? Like immediately I can just look at that and see it. Do you have to write all this stuff down, or can you just like kind of check through it in your head? You can just kind of check through it in your head. When we look at the three-dimensional case, it'll be a little bit more important that you're kind of following the same steps because it's a little bit more complicated. There's a fourth outcome that can happen. But we'll just pause there. That's still a day away. Okay. So to find the intersection then. What we're going to do is we're going to set R1 equal to R2. So I'm just going to set the two vector line equations equal to each other, just like we would for like a substitution problem, right, where we set our two equations equal to each other. I'm now going to do the vector operations on each side. So that's a scalar multiplication and a vector addition. So when I do that, I get like 2 plus 2s as my x component and negative 2 plus 4s as my y component. And I do the same thing on the other side. And I know that two vectors are equal only if their components are equal, right? So that's going to form a system of two equations. So I'm just setting the x components equal to each other and the y components equal to each other. And those have to be equal simultaneously, right? The same values of s and t have to make them equal at the same time. So that's why it's a system. What I'm going to do now is just rearrange my system so the variables are on one side and the constants are on the other. So I'm going to subtract 3t from both sides and then subtract 2 from both sides. And on the other one, I'm going to add 5t to both sides and then add 2 to both sides. So there's my system all set up nice and neat. Remember, for the system to be formatted properly, to type this into a matrix, the variables have to line up vertically. So s's have to be on top of s's, t's on top of t's. The equal sign has to be in the same place, and constant, or the solution has to be the last thing. All has to line up. What we'll do now is we'll go to the calculator and type this system in and just use a matrix to solve it. So second, and the matrix button, we'll go over to the edit command. I'm going to pick matrix A. That's a 2 by 3 matrix. And all I'm going to do is type in the coefficients. So 2, negative 3, 1, and then 4, 5, 3. Once I've done that, I'm going to exit out to the main screen. Then I'll go back to the matrix menu, this time to the math tab. I'm going to scroll down the list in the math tab till I find the command RREF. And I'll perform that on the matrix A. So I'll go back to the matrix menu. Under the names tab, I'll retrieve matrix A, close my parenthesis and hit enter. So that's my solution. That looks pretty gross though. So I'm going to use the fraction command on that. And I get that the value for s is 7 over 11, and the value for t is 1 over 11. Elena, is that okay? You guys got the calculator piece squared away, or do you need some assistance here, Giselle? Okay. Are we done, though? No, right? So the S and T is not the X and Y coordinate of the point we're looking for. What it is, it's the parameter for the equation R1 and the equation R2 that'll give me the point of intersection. So what I'm going to do now is I'm going to take S, which was the parameter for R1, and plug that in. So what do I get there? I get 2 plus 2 times 7 over 11, and then negative 2 plus 4 times 7 over 11. And then whatever that simplifies down to, that'll be the point of intersection. If I do the same thing with the t into R2, I should get the same vector out of this. So what's that going to be? 14 over 11 plus 22 over 11. So that's going to be 36 over 11. And then 28 over 11 plus negative 22 over 11 gives me 6 over 11. I think. Mental math with fractions is hard at 8:06 in the morning, but should be able to do it. That is correct, according to the answers. So that's nice. And again, I recognize that process is a little bit, it's a lot. The good news is it's the same process you use in 3 dimensions, essentially. And all of these little steps along the way are just steps that we would do for other kind of tasks in the chapter, like in the homework or whatever. So it's, like nice that most of this stuff is still like, comes up other places. It's not like you're learning this as a standalone, right? That it overlaps with a bunch of other stuff. I don't know if that makes it better or worse. To me, that's better because it's like, oh, it's just this skill again. Maybe it's worse because it's like, oh, this feels like the same thing as this thing. It kind of is. I don't know if that makes things better or worse for us, but is that okay, Elena?
Yeah.
Cool. Who's next? Happy to do some more? These two are both rather involved. These were good ones to pick, as they're not trivial. Giselle? 58?
Mm-hmm.
Sure. Okay. So 58 asks us to determine whether the following point lies on the given line. So this is the procedure you do to check to tell the difference between something that's coinciding and parallel. This is the procedure. So this same skill is something that would come up again in that kind of branch. What I'm going to start by doing is rewriting this as a like IB component form problem. Because right now it's in this kind of annoying a linear combination form, right? Okay. So if I take a look at this first vector, really I have 0i minus 5it. Let's write it plus a negative. And in the second, I have negative 8j plus 4tj. Oops, I wrote 4jt. Everybody's okay with just what I've done there? I haven't really done anything. I just kind of rewrote it. So the stuff without the i's on it, or the stuff without the t's on it, I should say, I'm going to group together. And the stuff with the t's on it, I'm going to group together. So this first vector without any t's on it is just going to be my point vector. The second vector with the t's attached to it is going to be like my slope vector. Remember that the vector I is just the vector like 1, 0. So it's just the x component of a vector. And j is the vector 0, 1. So it's just like the y component for a vector. So 0i minus 8j is just the vector 0, negative 8. Everybody's okay with that? So what I'm going to do now is I'm going to plug in the point that we're interested in, and we're going to see is there a value for t such that I can get the output of 15, negative 20. So basically I'm just going to set up the system. 15 has to equal the x component, and negative 20 has to equal the y component. So if I solve that first equation for t, I get t has to be negative 3. And if I do the second one, I'm going to add the 8 over. That makes it negative 12. And divide by 4. So I get negative 3 for both. So the answer there is yes. The point negative 15 or 15, negative 20 lies on that line R1. If the t's were different, we'd say no, that the point doesn't lie on the line, because there's not some parameter t that can generate the point in question. So this is how we tell the difference between parallel line and coinciding line, is you take the point vector from R1 and plug it into R2 and see if that point lies on the line. Because if they have the same slope and one point from one line lies on the other line, all of the points have to be on the same line, right? That they're just the same line. So again, this is a nice, because this procedure just becomes part of a bigger procedure, right? This one specific skill. Now I went through like a lot of rigmarole to get to this. It's also perfectly feasible for you to have gone, okay, so R is just negative 5 in the, or negative 5t in the x, and then negative 8 plus 4t in the y, and just be done there. Right? You're at the same spot we were here. Right? We just went there immediately. Now I chose to take my time going there to connect like linear combination form with this IB component form to try to re-explain what was going on, but like there's no reason you couldn't just look at this and translate it. The stuff that would attach to the I is in the X. The stuff attached to the J goes in the Y. That's all I need. Set it equal to my point and go. becomes a little bit more compact, showing your work doing it that way. But like, you miss like what is the connection between these different forms and like why can I do that? Which I wanted to explain before I showed you just like how to look at it and write out what you need. You know what I mean? Although in practice, doing it the short way is just, that's what you want to do. Because who wants to write that much? Not me. Not because I'm lazy, because I'm efficient. Others. Okay, cool. If more comes up later, we can always circle back and talk more on things. That's no problem at all. Today, we're going to be talking about 3D vectors. So, what do you think component form for a 3D vector looks like? X, Y, Z, yep. Oh my goodness, Mr. Kulak, are you kidding me? 3 dimensions, there's 3 components? Yup. That's it. Does it still mean the same thing where the tail of our vertex is at the origin and the head is at the point X, Y, Z? Yup. What's the IB component form look like then? Well, just the column vector, X, Y, Z. What's the linear combination form going to look like? Well, it's going to be x times the vector I, y times the vector j, and then z times our new unit vector is k. Why did we choose k? Just the alphabets, you silly gooses. I, j, k, where I is the vector 1, 0, 0, j is the vector 0, 1, 0, and k is the vector 0, 0, 1. Everybody feel okay with this? Not surprising at all. How do you suppose we do the magnitude for a 3-dimensional vector? Well, if you remember last time, we had the distance formula. What if our second point is just the origin? What's this going to turn into? X squared plus y squared plus z squared, all square rooted? Oh, yeah, of course. And again, that's assuming that v is written in component form. What if it's not? What if I've given you vector v as 2 points? How to write vector v? We do it the same way we did for a two-dimensional vector. We just do head minus tail. We just have a third component, but whoop-de-doo-doo! Okay, well that's easy. How do you think we add vectors if it's three-dimensional? What do you think? Yeah, the same way. We just add up the components and bada boom, bada bing. And again, if your penmanship is tough to tell the difference between U's and V's, like just use A's and B's or something. Like use two letters that you can't goof up what they look like on your sheet of paper. I get it. My penmanship is less than spectacular a lot of time. Great. So obvious. That's super obvious. So far, this has been like a big nothing burger of a section, right? More or less, this whole section is kind of a nothing burger, but that's good, right? I love it. How do you think scalar multiplication works? So I'm multiplying vector v by k, some real number k. How do you think that's going to work? Yeah, it just multiplies each component. You got it, dude. I love it. What do you think the vector additive inverse looks like? Well, it's just negative v, which means we just negate all its components. Right? Still the same thing as two-dimensional, just with a third component, which means that we can do vector subtraction the same way. Everybody's okay with this so far? If we're doing a dot product, how's that going to work? How did it work? How does dot product work for two-dimensional vectors? Multiply the x components, multiply the y components, add them together. 3 dimensions, what do you think it's going to be? Multiply the x components, multiply the y components, multiply the z components, add them together. Yeah. And because of this, because it's really the same process, so all of our properties of dot products from 2 dimensions still hold in 3 dimensions. So again, if you didn't remember what those were, because you probably don't, because it's been a couple of days since we talked about this, those were the list of properties again. Okay, what thing haven't we talked about yet for 3 dimensions that we have in 2 dimensions? What piece haven't we talked about yet? Starts with a D. Direction, yeah. Why haven't we talked about this yet? Is it going to be a clean conversion? No, right? In 2 dimensions, what did we describe the direction as? Just that standard position angle, right? Which relied on us operating on the XY axis in 2 dimensions. So instead of the direction being like circular based, and if we extend this into 3 dimensions, it's going to be spherical based. How many angles are we going to need to navigate on a sphere? What do you need to know to navigate on the Earth's surface? Latitude, longitude, 2 angles. Same idea. In practice, we don't do this. From a mathematics standpoint, we don't do this. It's not efficient. It's not a good way to communicate this information. So we're not going to do this in this class. If you're becoming a pilot, yes, sure, that's something you'll deal with. It's beyond the scope of this class. We're not going to talk about direction in a 3-dimensional standpoint outside of drawing the picture of the vector and putting an arrow on it, which we talked about last time, right? So worth mentioning. All right, so let's do a numeric example here of some of the stuff. So this example says to find and graph the vector W, which is equal to 2 times the vector U plus the vector V, given that the vector U is -2, 4, 7, and the vector V is the linear combination form 7i minus 6j minus 9k. What's the first thing that Mr. Kulik would do? I'm going to rewrite V in component form. What would V be as a component form vector? Great, 7, -6, 9. The coefficient for I is the x component. Coefficient for j is the y component, the coefficient for k is the z component. So w then is going to be 2 times -247 plus 7, -6, -9. So 2 times -4 is, or 2 times -2 is -4, plus 7 is 3. 2 times 4 is 8, plus -6 is 2. 2 times 7 is 14, minus 9 is 5. So there's the find part. Everybody feel okay doing that? Super easy, right? Same thing that we've done in 2 dimensions. Now let's graph this. We talked about this last time. Where did that go? Oh boy. Okay. Try that again. Oh, there it is. That's not where I wanted that to pop up, and not the color I would want for it. Okay, try again here, one more time. Well, fine. No, I'd hate this. I don't like this, what they gave me. I'm done. I don't accept you. Let me grab. We're just going to screen cap that from before. That's much nicer to look at. Sorry, guys. We'll get this. Be right with you. There we go. All right. So, what do we do? How do we start? We want to draw in our tick mark, so we need 3 on the positive x, and then 2 on the positive y, and then 5 on the positive z. Okay? And now we're going to plot the point 3, 2. So to do that, we're going to kind of origin, just going to kind of draw a parallelogram. Everybody's okay with what we've drawn there? And that's like the point 3, 2. Now what we do after we've done that, we lift that entire plane that we've drawn into 3 dimensions. So I start at the origin and I draw up 5 units in the z. Then I do the side parallel to it. Then I just kind of estimate and which of those is my solution? It's that But that's not a vector, that's just a point that we've drawn. How do I turn it into a vector? I draw the arrow from the origin to my point. Everybody okay? Remember doing this yesterday? Not yesterday, or last class. The every other day thing still kills me in terms of everything is yesterday. It's like, nope, we didn't see you yesterday. Overall, three-dimensional vector operations, easy, right? It's the same as, works the same way the two-dimensional stuff was working. All right, let's talk about three-dimensional vector line equations. We'll probably take more than one day doing this. So when we did this in 2D, we had like our vector line equation was like point vector plus some constant times the slope vector, right? The slope exists in 3 dimensions, though. Not really, right? Not really, because you have like X, Y, and Z all kind of changing, so it can't be just like rise over run. It would be like rise over run over height or something. Like, does this make any sense anymore? So it's impractical for us to try to translate this back into like a Cartesian equation of a line. Because even if I write an equation like 3x plus 2y minus 6z equals 5 or something, that's not the equation of a line. This is the equation of a plane. So a vector line equation becomes really, really helpful for us in 3 dimensions and higher, because we can easily represent these concepts with a vector equation in a way that we can't easily do with a Cartesian equation. So it's ostensibly the same equation here. So for some point P naught on the line R with the vector R naught going to point P naught, and the vector V in the same direction as line R, the equation of R can be given by R equals R naught plus TV, where T is just some scalar multiplier. Same form as 2 dimensions, right? Same equation as 2 dimensions. So how am I going to turn 2 3-dimensional points into a vector line equation? Well, getting R naught is going to be easy. There's 2 obvious choices for R naught. There's actually infinitely many, but 2 that would like practical choices. What would those 2 be? Well, just vectorizing one of the points that's given to me, right? Everybody's okay with that? If R0 is a point vector, I'm just going to take one of my points and turn it into a vector. Yes, Hannah. Of course. How are we going to get the direction vector then? How am I going to find some vector in the same direction as this line? Or opposite direction? Well, you won't want to do the inverse of one of the point vectors. What you'd want to find is the vector from that point to that point, or, in the other direction. It doesn't matter. That's the easiest way to do it. Now you have a vector with the same direction as the line that's passing through those 2 points. So you would say 5 minus -3, -2 minus 4, 6 minus 1, so 8, -6, 5. Or you could have written it the other way, -3 minus 5, 4 minus a -2, and then 1 minus 6. What do you notice about those 2 V's that we found? But just the opposite sides, right? Not surprising. If I take the same vector and go head to tail, and then tail to head, all you have are vectors going opposite directions, which we know is just a negative sign. So one possible answer, I could write that, and there's actually 4 possible answers based on what we've written here, right? I could pair this one with this one or this one, and I could pair this one with this one or this one. So there's like 4 possible answers just from the information that we wrote down there. You only need one. In general, what do you notice here? Basically the same process, right? Isn't head minus tail just basically y2 minus y1, x2 minus x1? Right? Still just the same thing we did before in 2 dimensions. And that's lovely. I like it when it's just like the same thing. Let's then ask to determine whether this point lies on this vector line equation. What do? Well, same thing we did in 2 dimensions. We just did an example problem like this, right? Giselle, this was one that you asked about, I think. So what do we have here? We have to see the system -5 equals -3 plus 1t, 6 equals 12 plus 3t, 11 equals 7 minus 2t. So if I add 3 over, t is -2. If I subtract 12 over, I get -6, and then divide by 3, I get -2. If I subtract the 7 over, I get 4, and then divide by -2, I get -2. Since those are all the same, yes, the point -5, 6, 11 lies on the line R. And we're going to stop here. The next section's a big one. I don't want to get into it. It's better to do it all in one setting. This feels like enough. What can we do up to now? Probably 118. So what are we at? We were at 88 before. Okay. All right, so let's sort out what's going to be due Sunday, right? Let me pull up my stuff. Because this needs to be reasonable, right? Mr. Kulik's not going to ask you to have like 100 problems due on Sunday. So I think I like 41 to 88 for this Sunday. That's what, the 5th? And then next Sunday would be what, like the 12th? We'll have 89 to the whole shebang, probably 122, but 118 so far. Everybody's okay? End of next week, beginning of the week after, probably in that range. Definitely want to wrap this before we leave on that long break, because I don't want this all dangling over there, because this is kind of complicated and it'll fade a little bit on you. So that's my goal, is to make sure that this is done before we go. The following chapters I think are not as difficult, because it's kind of the same thing over again, which is I'm okay with. I would be okay with as soon as, like, oh, we're just new names for the same thing, huh? All right, cool. I'm good with that. But this feels like enough for today. So you guys have what, like 20 minutes or something left? Get a start on something, right? Let's get some stuff done.